So at this point, we are ready to talk about resolution in first order logic. The main mechanism is not that different. Okay, we look for literals and the literal itself in one clause and its negation in the other, and then you merge them together, and that is the same. However, of course, there are more details here. First of all, a first order logic statement should be put in clausal form. Okay, so this is similar to what we did with propositional logic. Essentially, you need to eliminate implications, by conditionals, etc. You get rid of all those. You just need ands, ors, negations in your statement, and you essentially put your statement in pre-next normal form. Okay, quantifiers at the beginning and the matrix at the end without any quantifiers. And inside the matrix, you do not want any conditionals, any implications. You just want ands, ors, negations. Okay, and then you put that into just actually also separate premises if you have ands in between. So put all the premises in clause form. Then make sure the variables are standardized. If you remember, this was assigning different names to variables that are related to different quantifiers. So make sure that your variables are standardized. That means for different set of, uh, even in different premises, if you have different quantifiers, use different variable names so that they are not confused. Okay. So different variables, a different variable associated with each quantifier. Number three is Skolemization. Okay, and here we are going to remove existential quantifiers. We are just going to name the values that make a predicate true, and it will just get rid of existential quantifiers. Okay, so there exists an x, p of x, this becomes p of k. Simple as that. Okay, we do not care about how many x values satisfy this. We just come up with a new value, a new constant k, which we call a Skolem constant. Okay, and we just write p of k instead of this. And in this way, we will eliminate all existential quantifiers so that everything that remains are universally quantified. If you have them together, there exists an x for all y p x y, let's say. I mean, this is a general statement, p of x, y. You can consider this a large statement, a compound statement, let's say, involving other predicates. Here, you just get rid of this existential quantifier and replace that the variable associated with it with a Skolem constant like this. Okay, so it becomes for all y, pky. You get rid of the existential quantifier. Um, the third case, the case with for all x that exists a y, pxy. Now, the existential quantifier now is inside the universal quantifier. If you remember our discussion from earlier, the order of these quantifiers when they are of different kinds is important. So I cannot switch them around, okay? But in this case, you cannot simply replace y with a Skolem constant and be done with it. We will talk about this case a little bit more later on, just in a minute, okay? But when do you do that? Essentially, what you have done is you have gotten rid of all existential quantifiers and you replace them with Skolem constants or Skolem functions, as we will see later on. So you just instantiated the quantified statements, and what remains is just universally quantified statements. Since we have just one kind of quantifier, at this point, we will drop them, okay? All variables are universally quantified. So instead of a variable, whatever you put, anything will work, right? Because it's universally quantified, and that means any value you put in for a variable, that the result will be still true. That's what universal quantification means. So we just drop the universal quantifiers at this point, okay? Finally, put the resulting statement in conjunctive normal form. What does that mean? If you have ands in your premises, break them apart into multiple premises. Okay, so in your premises, you just want to see ors or negations. So you'll just have clauses involving literals, maybe their negations, without any quantifiers. So at this point, you are ready to apply resolution. Then two clauses can be resolved by finding complementary literals, as we have done with propositional logic statements. But here, of course, we have defined the concept of unification. It wasn't a random definition, and we need that at this stage because with propositional logic, you have something like P or Q, and let's say not P or R. This will lead to, this will be resolved into Q or R. You resolve these two, right? But here, with first order logic statements, you might have some predicates that are not identical, but may be unified. Okay, so in that case, we say that first order literals, I mean, in proposition logic, our literals like are P, not P, Q, R, not Q, not R, etc. Those are literals. But in first order logic, we have predicates, and some of those predicates involve variables. Some of them involve values, but some of them involve variables. So first order literals are complementary if one unifies with the negation of the other. Okay, so what does this mean? We are going to come to that in a minute. Let's continue, and let's go back to this state here, this procedure. We are in Skolemization, but as I said, if you have this form, it's a little bit more complicated, and let's see why that is so. We have seen that there exists an x, p of x, it can be written as p of k, where k is a Skolem constant. Similarly, if you have there exists an x, for all y, p of xy, you can write this as for all y, p of ky, where now k is a Skolem constant. However, if you have for all x, there exists y, pxy. You cannot just simply write this using a Skolem constant. Be careful here. What does this say? It says for all x values, there exists a corresponding y to x, that has the relationship with p with this particular x. This is important, okay? For any x value you pick, there is a y value that satisfies this, but that value is particular to that specific x value. It's not universal, okay? So the y value for each x is potentially different. That is the key here. Therefore, if you just naively Skolemize this using a Skolem constant, you can write for all x p x k, okay? Then what does this mean? This means there is a particular k, a specific, a unique k, that has the relationship p with all possible x values. This doesn't capture this behavior because you remember the y values, they exist corresponding to each specific x value. So for every x value, you have a particular y that is potentially different from the others. But here, if you write it like this, okay, you are making a mistake because now this k here, whatever k is, you claim that the k value has this relationship with all x values. Okay, so this is a mistake because you are missing that one by one relationship between different pairs. Now, in this case, instead of a Skolem constant, we use a Skolem function to, to signify that relationship between the two. Okay, and this function will depend on x. So for each x value, it will take a different value, okay, rather than a Skolem constant. It will not be a constant. For instance, take the statement, for every pet, there is a person who cares for it. Okay, let's Skolemize this statement. First of all, let's express this in first order logic. It says for all x, if x is a pet, so essentially this is my domain, then there exists a y and y cares for x. That's simply what is given to us. Okay. Now you can first of all put this in pre-next normal form, which I'm not going to do, but you can just do it yourself, which is not that difficult anyway. So this is for all x there exists a y, not pet x or cares y x. Okay. Now you see this has the same structure with this. Okay. So here we cannot write for all x, uh, not pet x or cares kx. If you write this, what you are saying is there is one single carer k that takes care of all the pets. Clearly, that is not what we are trying to say. So what you write instead of this, using a Skolemization function, you write for all x, not pet x, or cares owner x x. This is my Skolemization function. Instead of a Skolemization constant k, I put a function here. I called it owner. That's my naming. That's my preference. Okay, you could have written here f of x. You could have written k of x. You could have written minder. You could have written sahip x. Okay, that's just the name, but it has to be a new name. Of course, it doesn't. It has to be non-existent in other definitions. Okay, so I'm in this way I'm associating the result, the value this function will take with x by making it depend on x. Therefore, that one-to-one behavior will not be lost. Okay, so this is how you Skolemize this type of quantified expressions.